Are in 4.2 with us. We're on page 100. Again, I am breaking into your room in the middle of the night. It's 3 a.m. I wake you up and I say, Kirsten, what is Newton's second law? And she says, oh no, she doesn't remember. Fama. Well, it's like she's calling me out. That's some sort of swear word, it sounds like, right? F equals what? M A. Newton's second law. Kirsten will forget now. F equals ma, right? And let's review. F is what?
Oh, force.
Force. Come on, friends, stay with me. What's M?
Mass.
Mass. A is? Okay. And again, this is Newton's second law that basically is telling us if I want to put a force on something, or when I put a force on something with mass, it's going to accelerate, right? If something is accelerating, there must be a force on it. Does that make sense? And we just assume everything has mass. We can certainly go into some of the theoretical thoughts of, well, is there actually pieces that don't have mass? There must be something somewhere, I don't know, there's a whole lot of mass in the universe that we can't explain. We call it dark matter. Okay, but that really is to me, it seems really kind of crazy, because we just basically made this stuff up because our calculations show there should be more stuff than there actually is. So we just call it dark matter. Okay. We could have done it wrong, and they checked it many times, and they said there's certainly something missing there, so that's where this comes from. But we call it dark because we can't actually see it. It's not producing some sort of spectrum that we can actually see and analyze. So, yes, sir? Sure. So for this, remember what our units were for force? Does anybody remember? Newtons. A Newton, if I'm going to use Newton as my force, and Michael, there are tons of units for force, but we're going to use Newtons for the most part. In order to do that, the mass must be in kilograms, and the acceleration must be in meters per second squared. Because that's what a Newton is. Please hear me. Newton has to be kilogram, meters, and seconds. It cannot be anything else. Right, it is a literal combination of those three units together. A Newton is a kilogram, meter per second squared, which is just simply multiplying those two together. Does that make sense? Again, this is chapter 4.1, review. So today, all we're looking to do is take this acceleration thing and give it a name. Talk about a specific kind of acceleration. And when what we're talking about is gravitational. Gravitational acceleration. And this is so important in the world of physics that we give it its own letter. Like you want to be a cool thing in the world of physics, you like get your own letter, right? And this is so cool, we call it G. And it is a little g. It's not the big G. A big G is a gravitational constant that Sir Isaac Newton came up with. We'll talk more about that in the future. Little g is gravitational acceleration. And you know little g as what number? 9.80 meters per second squared. And this is the amount of acceleration that is present from the force of gravity. Gravity is a field force, right? In other words, it doesn't actually push on you. There's no physical gravity person yanking you down to the ground. Okay? It's a force that occurs over a distance. That's a field force. Whereas if I'm actually punching on Lucas's shoulder, what kind of force was that? Do you remember? Contact force. There's actually physical contact between the thing providing the force and the thing receiving the force. Because then Lucas would, of course, punch me back in the face. I got you. Okay, I'm with you. All right? So therefore, gravitational acceleration is g. So are you comfortable then that when gravity works on some mass, there's a force that's there, right? So, again, if I go back to this F equals ma, right? We are giving g as my acceleration, right? And we are saying m is mass, which doesn't change, right? So what do we call the force that gravity puts on us? Does anybody have any idea? I'll give you a clue. It's in big, bold letters right on page 100 at the very top. We call that our weight. So the weight of an object is the amount of mass it has times the gravitational acceleration. And again, this is where in the world of physics we differentiate between mass and weight. In the lay world, right, you talk to your friends, they won't differentiate between mass and weight, right? But weight is an actual force from gravity. And again, I use this example all the time, but it makes perfect sense. I weigh 220 pounds. That's my weight, right? My mass, I want to guess, is about 70 kilograms. I have to actually do the math to see what it is. I don't know. Okay? If I go to the moon, right, does my mass change? My mass does not. Again, unless I walked there or flapped my arms to get there or something and burned tons of calories. Okay? But if I were just transported there, my mass does not change. But would my weight change? Absolutely. Why? Because the force of gravity is less there. The acceleration, not the force, the acceleration of gravity is less on the moon. It's about a fifth of what we have here on the Earth. Because the moon is about a fifth the size. Because force, when I say force, I'm meaning weight. So yes, it is, but we're talking about acceleration here. Okay? So I want to make sure you understand, mass is something that does not change. Again, unless you somehow move it or remove it or do something with it. Even when you react it chemically, right? The law of conservation of mass says nothing goes away. It's all conserved. Okay? We could take mass and turn it into energy. That's what Mr. Einstein said, right? With E equals mc squared. That those two things are the same. Energy and mass are the same. If I take just a tiny little bit of mass and I turn it all to energy, we call that an atomic bomb. Right? That I'm taking and splitting this and taking all that mass and turning it into energy. Whew, very powerful. Right? A cup of water could like explode a whole city. There's that much energy in that little bit of mass. Are you with me? It is impressive. All right, so let's do some problems. And again, if I want to use my units here, weight has what units? It's a force. So what units does it have? Newtons. Weight is newtons. Now I realize you and I use what term for weight? Pounds. Okay? That's another measure of weight. I don't know off the top of my head, to be honest with you. We could certainly figure it out. Yeah. What's the units for mass? Kilograms. What's the unit for gravitational acceleration? Meters per second squared. All right, so let's do some problems here. If you want to look at this example problem on page 101, okay? Kieran holds a brass cylinder in each hand. Cylinder A has a mass of 100 grams. Cylinder B has a mass of 300 grams. We want to know what upward forces do his two hands exert to keep the cylinders at rest. Let's deal with that first. Okay? So I've got A is 100 grams and B is 300. Is that right? 300 grams. All right. So I want to know, we're trying to find what upward force. What is the force that his hand has to put on? So let's draw like a little diagram here. I am a terrible drawer. Okay, and he's holding the weight here in his hand. We cool? Color it in. Beautiful. Okay, that looks like a terrible bone or something. I don't know, it's horrid. What force is acting on this weight? The force of gravity. Gravitational acceleration pulling it downward. Are we cool? So this is the force of gravity. But we said, is the weight in motion? No, it says we're holding it still, right? So therefore, what must also be happening here? There must be a force pulling upward. So the force of his hand that's pushing upward. And what do we know about those forces? They must be equal. Because the net force is zero, right? The object is not accelerating in some way. We'll come there. We'll give 1 second. Are you comfortable then if we wanted to know the amount of force he's pushing up? all we have to do is just simply calculate the force of gravity, because those two are the same. Does that make sense? Because we don't have any good information about his force, but we can certainly do some good calculating about the force of gravity, right? So if this is container A that we're dealing with here, how would you calculate the force that gravity is pushing on this container? Okay, well, our force is equal to what? What's our equation for force? Mass times, and since we're dealing with gravity, do you mind if I put G? Okay, F equals mg. Okay, because I want to make sure you hear me, and some of you were starting to go this way. I want to make sure you understand this. If I say force of gravity, that is not 9.80. That is the acceleration due to gravity. The force of gravity is that acceleration times the mass it's affecting. Does that make sense? So let me say that again. We'll make a pause here. The force of gravity is in newtons, right? It would be the mass times gravity is going to give you the force. Okay? If I'm saying the acceleration of gravity, the acceleration is 9.80 meters per second squared. That's g, right? Please hear me. Those are two different things. Two totally different things. You have to use g to find the force. You have to use the acceleration to find the force. But they are not the same thing. Right. This 9.80 is the acceleration of the Earth's gravity. And we're assuming the physics problems we do, unless they tell you otherwise, are done on the planet Earth. Sometimes they'll take you in space, but most of the time it's here. Does that make sense? Okay, back to our regular scheduled programming. We want to calculate A, the force that this gravity is pulling down on A, because if we know that, we know how much force he's pushing up to hold it still. So, what number was I going to put in for M? I got to change it. Why can't I just use 100? It's grams. Please watch those units. Please, please, please. Your textbook loves to give you these stupid problems where the units are different than what you need, and you have to convert them. All right, so please be careful. So 1,000 grams in 1 kilogram, right? So 100 divided by 1,000 is 0.100 times, what's G? 9.80. Okay? So, therefore, F equals what? 9.80 times 0.1. Somebody got it for me? Pop it in for you. So we got 0.98, right? How many significant digits should we have here? So we used 4 here, we used 3 there. So I'm okay if you point 0.980. And what are my units? My units are newtons. How about for B? For my container B? It's again going to be the same equation, right? F equals mg. So F equals 0.300 times 9.8. And when I do that math, I get 2.90. And what's my units again? Newtons. Unit for force is always newtons. Okay, they do some little showing you the second half of this problem there on page 101. They show you how the acceleration is the same, right? They basically switch this equation around. They take F equals mg and they switch it around to get g by itself is F over m. And so they take the force that we just found, right? Are you with me? And they plug in the masses, and you find out that both of those give you 9.80. That's their point, is just showing that, hey, mass doesn't matter. This is mathematically showing you mass does not matter. It still accelerates at the same acceleration, 9.80. Any questions with these? Because the problems we're doing here is just simply we're calculating forces, or we're calculating acceleration, or we're calculating mass. If I know acceleration and force, I can find out how much mass this thing had. But are you comfortable it all boils back down to that equation, F equals mg? And I can flip it around to get g. I can flip it around to get m, right? M would be F over g, right? Doesn't matter how I flip it around. It's still the same equation. Make sense? Any questions there? Yeah.
We're using F, and then we're going to change it to
Newtons, yeah.
why not just say
Because we're using this, just like we say that m is mass, right? But mass is kg, right? That's the units for mass. It's the same thing. N are the newtons. That's the unit for force. So we use force as the symbol in our equations, but the units that come out of that is newtons. Does that make sense? And there's actually oodles of different units we could use for force. There's lots of different ones. Again, pounds is a unit of force. How many pounds I weigh is a unit of force. Does that make sense? So, but we use newtons. That's just what we use in this.
So how do we know you have different
Yeah.
How do we know?
It's going to be based upon what unit you're given. And again, in this class, 95 or 90, even 99% of the time, we're going to use newtons for force. Yeah. It could be kilonewtons. I mean, we could put prefixes onto it and make them bigger or smaller if we wanted to. But newtons is pretty much what we use. It's a good question. Okay? So, what I'm asking you to do today is to do, this is a 4.2. This is on page 101. And I'm asking you to please spend your time right now doing numbers 16 through 19.